So welcome to our fifth video in the B07 using R packages series. Here we're using Bioconductor, which is a very powerful suite of bioinformatics packages that we can use. Bioconductor can be called using this particular command. We install .packages and we install a tool called BioC Manager. BioC Manager is a particular nickname for Bioconductor in essence. Previously, BioC Manager was a different nickname that was used to refer to Bioconductor. It was called BioC Lite. So you may find code on the interweb with BioC Lite written in there. Don't use that code. It's old. It won't work. You'll need to use BioC Manager to run things. We can call BioC Manager, which is a package, in the same manner as before. We have BioC Manager here at the start, then two colons. Then we have our function here, and we're calling MSA, which is a multiple sequence alignment tool, and we're going to install that, which is handy because we're going to look at sequence data next. So we activate that library, and then we can move on to the next stage. Next stage involves downloading another package, which is in Bioconductor, called biostrings, which can deal with sequences, RNA sequence, protein sequence, whatever type of sequence that you're looking at. It has functions that will help you manipulate that. So we activate biostrings as before, and then we read in that a string set, an example data, which is on the end drive. And this is lumpy skin disease viruses, just 5,000 base pairs or thereabouts each. And we're going to send that to a variable called mys, which is an object containing those sequences. So kind of like a FASTA file in essence. There's 41 of them in there. They contain the 5' ends of the de novo assembled genome sequences, so they're not always exact in their alignment, and they have a lot of diversity within there. So what we can do to explore that is use our functions to get a grip on whether these actually are related to each other. Sometimes samples are mislabeled, and we're going to look at that next. So we're going to read them in as my sequence data, whatever. At the start, we're going to check the structure to check it's okay. Then we're going to take MSA, that tool we had at the start, and we're going to send our file as input, and we're going to use +omega to align those sequences. There are other alignment tools in there as well, but +omega is good at tolerating missing data. So if you try a different alignment method, it may not work necessarily if there's missing data. So we're going to send that to my alignment. Note that obviously we're not optimizing our alignment here. This is just an illustration of how you can align sequences if you wish to do so in R. If you actually want to align things properly, there's quite a few additional steps to think about. But we can check our alignment by printing it out and having an eyeball to see if it actually worked properly. If you use something that's very divergent, obviously it may not align properly at all. If you scroll up and down this big alignment, you'll find that there are parts of it that are pretty good. This section is from 3.5 kb in, where you see we have 41 samples listed there, not all are shown. And then the only real variation here is this kind of indel here for certain samples. We see that with the consensus at the bottom is that the sequence identity is very high in this particular segment, but you'll find other segments where it's not great at all. So what we can do next is take our alignment and we can export that as a file. Another option is to use another package. There's a lot of packages. sequenr is another tool that allows us to view and manipulate sequence further using other functions. This is just an inbuilt package. It's not in BioC Manager, as you can see. So we're going to take our alignment, and so we're calling it a sequenr alignment just to state what type of alignment it is. And then we're going to use the conversion tool to make my alignment my A. And then we're going to send that down here to construct a distance matrix between each sample pair and populate that in a distance matrix. So we just get a square table of each of the samples and their relative distances based on this 5 kb segment. So if you view our alignment to look something like this in our distance matrix, for each sample A, B, C here, for A versus A, obviously the distance is 0, the same for B versus B. But for A versus B, and likewise B versus A, you might find that there is some fraction of bases that are different. So typically these functions give a range of values between 0 and 1, where it simply denotes the fraction there. It may give the upper or lower diagonal only because this is symmetric. So could look like this. So we have these samples, and then we have other samples, and we're saying obviously this is its distance from itself is 0, but its distance to the next one is 0.03, whereas for other ones it might vary a bit. Another tool we can add on to this, looking at our distance matrix, is to take our original sequence alignment, and we can draw a phylogeny. So we can use this package called ape, which can do evolutionary analysis. We can activate our library here and use this special function called plot.phyllo. The function plot will also work as well, but it's calling the one inside the ape package here. So to avoid ambiguity, you're better off using plot.phyllo because it's more intuitive for yourself. If you're rereading this code in a year's time, it creates less confusion. So we use the neighbor joining method, nj method, to construct our distance matrix, take in our distance matrix and construct a phylogeny from it. This is obviously just a quick phylogeny. It's not necessarily a good phylogeny. It may not even be informative, but at least gives a representation of the genetic similarity of these different samples. It's not optimized. There's a lot of steps we should consider for constructing a phylogeny, but it illustrates how R can produce a phylogeny if we want to do so. So we give it a title here. We're plotting a phylogram. So that's kind of the traditional method that you expect. We're changing the text size to be a bit smaller, and we're adding a root if it is possible. So we'll get something like this, and we'll explore this more in the demonstration video. So it's not a perfect tree, but it is a tree. If we, this is how it looks if you zoom in. So at least you get a sense of what's similar or what's dissimilar. You note that this tree is not, it's not rooted properly based on, say, midpoint routing or right-loop routing. It's simply by the order of sequences as they arrive in the FASTA file. If we did root it properly for the first 5 kb only, you get something like this, that this is the midpoint root for the first 5 kb only, and you see there is some structure there, that there's definitely different groups, different clades. If you look at the full alignment, you get a more resolved picture looking at this, where you can see there's more distinct clades that are definitely present. Or we're just looking at 5 kb only, because if you run the alignment for much longer, for a much bigger sequence, it just takes forever. So we're skipping that in our example. Another approach that we can use is called principal components analysis. So this is a way of taking our data, our sequence data, each of which theoretically each site is its own dimension. So in principle, it's n-dimensional space. However, many of the sites are correlated with each other. So we're looking at how they co-vary together. So sites A and B have an identical pattern that they only vary in the same set of samples. Then sites A and B are effectively the same and for all purposes. So see segments that have a similar phylogenetic pattern and other segments that have a different phylogenetic pattern. And if we look at those patterns across the whole sequence, we can allocate them to different correlated variables. So that's kind of what we're looking at here. We're looking at these variables that are correlated. So for example, height and weight are correlated. If you know someone's weight, you predict their height. If they're heavier, they're probably taller. If they're lighter, they're probably smaller. There's no causality inferred here. It's just simply, it's a good predictor. So we're taking these correlated variables, and if they explain a significant fraction of the total variation that's present, we can label these as principal components, also known as eigenvectors. So the number of PCs is far fewer than the number of original values, the sites. And what we typically do is look at the first 2 or 3 to look at the fraction of variation that they explain and how the samples arrange themselves over that space. So if you think about that, this whole process, what we're doing is a type of transformation. We're looking at the variance of y in a particular feature of interest. It could be a SNP site. We're looking at the variance of x and y together, and we're looking at the covariance to see how they co-vary together. Are they correlated or are they not? Can we measure that? the covariance is the measure is input into the correlation function calculation. So we're simply using the correlation function to calculate the extent to which they covary. So you can think about this, if we plot our data originally like this here, we have some noise that varies across different samples with no obvious trend. And then we have signal in this direction. What we're effectively doing is rotating this. So this becomes the x-axis down here. And then we can measure the extent to which there's noise across these samples up or down. So in terms of the steps, what we're doing with PCA is we're taking away 0 from each of the values, such that the new column mean is 0. So what this will mean is that the data is normalized. So basically, if you sum up all the values in a particular column now after it's normalized, the sum total present will be 0. Doesn't mean each of the values present is 0, but it means the mean, should I say, is now going to be 0. We then calculate the covariance, and simply covariance is like calculating the standard deviation, like the value minus the mean. So each of the values of x minus the mean of x, multiplied by each of the values of y by the mean of y, sum that up, and do that for each particular column. So looking at the covariance of x and y together to see if they covary or not. So we could take, for example, height and weight together. So the covariance of height and weight is the same as the covariance of weight and height. And that's simply each of the values of heights minus the mean of heights, and the same for weights. And we take the product to look at whether this is actually positive, which means that they're correlated, or negative, which means they're not correlated, they're anti-correlated, or maybe if this is simply equal to 0, then they're completely independent. And that also is very interesting if they are independent. So the next step is to explore the level of dependency, and then to compare the covariance to the variance individually of the heights and weights to kind of scale it to calculate our correlation coefficient here. So we're taking the covariance of height and weight together, divided by the variance of heights, and divided by the variance of weights. So for example, if the R square value is 0.1, we can say that they are positively correlated, where each explains 10% of the other's variation. It doesn't mean there's any causality there. Indeed, height and weight could be caused by another independent, unobserved feature. So next, what we do from this values, if we do it across all our different variables of interest, is that we're looking at the size of each of the principal components. So these contain a bunch of correlated variables, and we calculate for each of these an eigenvalue. So if we have a big eigenvalue, that might mean the biggest one obviously is PC1, principal component 1, the biggest one. The second biggest eigenvalue is PC2, and so on and so on. The third biggest is PC3. And these eigenvalues correspond to eigenvectors or principal components. So the eigenvectors contain the actual coordinates in one-dimensional space for each of the PCs and the dish where the samples are arranged. So the eigenvalues is the magnitude of each PC, and eigenvectors simply are the coordinates for a sample for each of the PCs as well. So we can then look at PC1. For example, this is the one with the largest number of snippets explaining the highest fraction of sample covariation among the PCs. PC2 is the second highest, and so on. Visually, it might look something like this. So this corresponds to the fraction of variation, the eigenvalue of PC1. This is PC2, this is PC3, and so on as you go further down. So you can see that the PC explaining the highest fraction of variation present is PC1, then PC2, and PC3. So what we're saying really here is that PCA is a orthogonal transformation technique, which transplants our samples into a new space where the PC1 and PC2 contain features that are correlated with each other individually. So PC1 variables contain a bunch of SNPs that are correlated with themselves, vice versa for PC2. And we're going to see the tendency of the samples to cluster in that space. And we can look at the fraction of variation explained by PC1 and PC2, and that's what we do in our functions here. So we're taking our function PCA proc, and we're getting the standard deviation to get the sum of all the variation present across all our eigenvalues. Note here that we're using PRComp, and that gives us more technical information. PrintComp, you'll often see for PCA, that's as good, but it doesn't give as much technical variation for looking at the fraction of variation explained per PC. So that's why I use PRComp. So you see it there, PRComp is our distance matrix we had before, all the way back here. Yeah, with the distance alignment in seqr. And now we're taking that distance matrix, containing the samples, and we're sending that to PCA1, and we're calculating the values for PC1, PC2, and PC3, the eigen values for each of them. What we're simply doing here is multiplying PCA1 for eigenvalue 1 divided by the sum of them all. So this is the sum of squares of all of the PCs all together, summed up together, and we're dividing. That's the denominator compared to the sum of squares for PC1 only. And we're rounding it just for visual clarity. And we do the same for PC2. Note here we got 1 and then we got 2 here instead because it's PC2. Same denominator as before. Then for PC3 is 3 and so on if you're going to want to go through all the PCs. But note after PC3 or even after PC1, you'll find the fraction of variation that's remaining is very, very small. And then we can assign colors for the samples if we want to as well. And that's taken from the dimensions of the alignment, which is just 41 in this case. And then we can plot out our values, and we'll talk about this more in the demonstration videos. What we do is we take a function called PNG. We give it a file name that we want to print out to in our current folder. If we want a nice plot, we give it a width and a height. Here, the width and height correspond to the sizes of PC1 and PC2. Not perfectly, because PC1 is very big and PC2 is very small. I'm using units of pixels. But this kind of gives you a sense that PC1 is bigger and PC2 is smaller. When we open this PNG function, we then have our code to write out to that file. So we're plotting PC1 here, 1, versus PC2. We're using colors as my call. XLab is the PC1 value, YLab is PC2. So PC1 should always be on the x-axis. The text size is 1. Here we have a title is PC1 versus PC2 across samples. The text size for the axis is increased to 1.5. The text axis for the axis labels is 1.5 as well. And we add a grid on top just to make it easy to view. And then we save our file at the end. So a lot of things going on here. And if you're unsure about how this works, change it, modify it, and see what happens. So if we plot this out, we'll get a principal components analysis plot looking like this. You can see sort of the colors and the points, the fraction of variation explained on each axis. You can see there PC1 explains a very, very large fraction of the total variation. So honestly, PC2 is not really worth looking at because most of it's on PC1. If you zoom in, you see something like this. So you can see across PC1, there's definitely a difference between some samples compared to other samples. And PC2, yeah, there's some samples that differentiate that on that axis as well. So in this longer video, we've looked at Biocity Manager and how we use Bioconductor and access those packages in there to do things that are routine, like align sequences, draw a phylogeny, create a PCA plot. All that is now possible by Bioconductor. So in the next video, we'll look at accessing databases as well.